Welcome back to Codex. Today we're happy to have a talk from Victor Albert from the University of Maryland and NIST. Dr. Albert is an expert in quantum codes and theoretical physics. Today he'll be speaking about quantum theory of molecular orientations. Take it away, Victor.
Thank you. It's a pleasure to speak to this community. I've edited my talk to make it more technical, not less, which as a physicist is much easier. So, there'll be some equations, which I think you guys like. I removed the experiment, so also probably something you guys don't want to hear about. But I do have backup slides, and depending on how this goes, it may be a very short few slides, depending on how many questions there are. I'm happy for there to be questions. Ideally there will be like maybe 5 or 10 slides that I'll go beyond that gets into the more technical, proof techniques. So this in collaboration with my previous grad student, Eric Kubishta, who did a lot of the heavy lifting of this and translated chemistry into a language that I could understand. And Misha and Lee, who are kind of chemistry-oriented friends who were consulting us along the way. Lee's in particular an experimentalist. And the main result deals with developing a notion of conjugacy for state spaces that you maybe would have thought conjugacy has existed for already. And the reason for that is because duality, Fourier duality, conjugacy, what have you, has existed for over 100 years for conventional state spaces like L2 of R, which I call the harmonic oscillator, and L2 of Z2, which I just call a qubit. And in both of those cases, you're likely familiar with the notion of a Fourier transform in the case of the harmonic oscillator and the Hadamard matrix in the case of a qubit. These are both can be thought of as kind of transformations that go between a position basis, which is the canonical basis you define on the space, and the momentum basis, which is the Fourier dual of the position basis. In the case of the harmonic oscillator, the position basis that you define is indexed by a continuous real number on the line, and it's not Kronecker delta orthonormal. The position basis states are not orthogonal. They're orthogonal, but they're not normalizable because they correspond to a state in a precisely defined position, which is impossible in the real world to do. And if you're anyone outside of math, you just perfectly well deal with these and write them as if they were regular states and get away with it. But if you want to be in math, then you can think of rigged Hilbert spaces and what have you and go in that direction. But Dirac didn't have to do that, so I'm good with just not doing that. And in all intents and purposes, these are perfectly fine Fourier dual bases. Now, Fourier dual kind of concepts also exist in electronic structure where there are wave functions that are localized in position, Bournier functions, and in momentum, block functions. And so here we're going to talk about a fourth paradigm, which deals not with linear positions of a particle, but angular orientations of a rigid body or specifically a molecule. And there too, you have states of angular momentum. The thing can keep spinning. It has a fixed angular momentum, or states of fixed orientation, namely the orientations of this pen I'm holding. And what was surprising here was something we found out along the way is that the momentum state picture has been very well studied for over 100 years by chemists. Now, this is not a surprise. The surprising part was that the position picture was not well developed, with the exception of a few cases. And why is that? Well, as far as I can tell, it's because chemistry experiments most often were in what's called the gas phase, meaning the molecules were all jiggling and rotating all over the place in your box. And so they were always associated with some states of momentum. And you could never really pin molecules down to some particular orientation. And so you didn't have to formalize a Fourier duality on these spaces because you didn't need it to explain the experiments. But recent experiments like trapping molecules and shining very strong electric fields to align them warrant this kind of investigation. And it's also kind of a fun thing from the math perspective because there's a lot of topology in these spaces of rigid body orientations with symmetries. So that's kind of the main goal that we do here. If anybody's confused about that, I'm definitely open for questions at this point. So if not, I'll just get into, okay, one more caveat. We have to add symmetries to the picture because molecules are small and they have nuclei. And when you apply certain proper rotations to them, SO3 rotations to them, then they come back to their same orientation. And the nuclei are identical, meaning you cannot distinguish, and they're indistinguishable, meaning you can't distinguish them. And therefore, there are certain symmetries that this molecule has that leave the nuclei basically invariant up to some permutation, and the nuclei have to behave a certain way under that permutation, aka satisfy spin statistics, either Fermi or boson spin statistics. And so this is all the thing we have to do here to classify these state spaces. We have to incorporate spin statistics and symmetry into the picture. Now, there are molecules that don't have any symmetry, like the one on the left here. And in that case, it's pretty much vanilla kind of rigid body physics, where none of these kinds of exotic features I'm going to highlight come in. And of course, macroscopic objects technically are not symmetric because they have many, many atoms. And if you rotate them to a configuration that looks as if it was the same one as the one you started with, the atoms don't actually align because there's like a bazillion of them. And so you don't actually impose these kinds of symmetry constraints on large objects that you do on these small molecules. Okay, so let's go into the first simple example. We're going to stick to 2D for the next few slides. So there, the possible rotations you can apply to these molecules are proper two-dimensional rotations. So they form the group U1 or the group SO2. And the state space of a pen, circularly symmetric pen, that's lying on a table is just the orbit of SO2 of this pen, which is basically just a circle. And so the pen is labeled by an angle. The orientation of the pen is labeled by an angle. This is the same space that's models the space of a hydrochloric acid, HCl, that molecule over there. And just to introduce the quantum notation with this simple case, we're going to use bracket notation because I don't know how else to do this. There are, again, two types of bases for this, a momentum and a position basis. And there's a Fourier transform that goes in between them. The Fourier transform is commonly referred to as the Fourier series. On the left-hand side, you have the expansion in the basis of position states, which is phi bra, which is just parametrizing a function on a circle, f of phi. So instead of writing f of phi, I write ket phi or bra phi f ket, thinking of f as an abstract vector and phi as a basis state. I keep using quotes for basis in case you are annoyed by the fact that I'm not going to the rigged Hilbert space formalism. On the other hand, you have a countable basis, so perfectly fine bona fide basis of momentum states indexed by an integer j. And again, f can be equivalently expressed in that basis using its Fourier series. And so then you have f of j, but to me it's just the same. It's bra j ket f. And there's a Fourier series that goes between them. So this is kind of the vanilla asymmetric rigid body in 2 dimensions. Now, what happens if we do have symmetry that we have to impose? In this case, we have a symmetry transformation, namely the one that, I'm looking for a dumbbell. We don't have a dumbbell, but let's assume this is a dumbbell, the one that does this on your table. So, okay, we're on a table, we move pi or 180 degrees, and the molecule is symmetric because its nuclei are identical, and so we have to impose this symmetry. This means that now we are going to be in a subspace of the state space, L2 of SO2, of the planar rotor that I showed you before. And this subspace is defined by a constraint on how you transform under the symmetry. The symmetry in this case is this x pi rotation. And how you transform is just the equation on the left here. The molecule state has to be invariant under the symmetry. It has to transform as giving a +1, aka as a trivial representation of the group. In this case, the group is just Z2, or the chemists like to call it C2. So what is the momentum states of this? Well, if you remember your integer labeled momentum states, and you observe that the transformation here that I'm acting on by the symmetry transformation is just -1 to the j hat, which is the operator of the momentum operator, which just labels the momentum states, then the states that have even parity are the momentum states of this symmetric dumbbell. On the position side, if you just naively take the Fourier transform, you get the position states, it turns out. And if you express those position states in terms of the position states of the original asymmetric case, then you see that the position states of the symmetric case are equal superpositions of the position of the asymmetric guy with its antipode. And that should kind of heuristically make sense, because we can't distinguish this and this because of the symmetry, and therefore we just superpose them. And if you're familiar with induced representations, this is an example of an induced representation. And I'll get to that in a bit. So again, the state space of symmetric objects that we'll study today are going to be subspaces of some bigger space that we can understand very simply. And we have constraints or conditions we impose on states in that big space to get to the small space. Okay? So now, the third class of molecules where things really get interesting is when you have not just the state space of all the different orientations that you have to deal with, but when the molecules have nuclei that are identical and spinful, meaning they have nuclear spin and they're identical. And in that case, the full state space now is not just the state space of all these orientations of the asymmetric guy that we have to constrain, but also the two nuclear factors, C2 and C2, of the two, in this case, spin 1/2 particles or fermionic nuclei of this hydrogen atom. And in this case, the physical requirement that's imposed by nature on the states of this molecule involves both the nuclei and the orientations behaving in a certain way. Namely, this symmetry transformation exchanges not only the positions, but also the spins of the nuclei. And this exchanging spins of nuclei requires that the nuclei satisfy spin statistics. In this case, the nuclei are spin 1/2. And so the nuclei, after exchange, have to spit out a -1. If this was deuterium, then this would be a spin 1 nuclear situation, and you would have a +1. In either case, it doesn't really matter what sign it is, but in either case, we have to worry about the composite space because we have a composite action of the symmetry. And so the constraint now involves both the rotational and the nuclear factors. The composite action of the symmetry here, you see, x pi now is not only -1 to the j hat, but it's also a swap action on the two C2 factors corresponding to the two spin 1/2 nuclei. So now with this constraint, there's two ways to get this -1. And this is how you get this ortho-para-hydrogen story that you may have heard of if you took any kind of quantum chemistry. The first way, called para-hydrogen, makes the sum come out of the nuclear factor. It superposes the nuclei in an antisymmetric state, up, down, minus, down, up, called a singlet. And that singlet behaves as the sign rep of the symmetry group C2. So the minus sign comes from there. Since the minus sign comes from the nuclear side, the rotational story then becomes the same as a dumbbell. There's a plus sign, there has to be a plus sign coming from that side, and that corresponds to only the even angular momenta like before. So in some sense, the para-hydrogen species can be thought of as a dumbbell with a dangling nuclear singlet spin, nuclear singlet spin state. The other way to do the sign is when things get interesting. Here the sign is relegated to the momentum side, the rotational side, and that necessitates J to be odd. The nuclear guys are in the triplet in the symmetric config space, and so the rotational side is now odd, and this is not something you can ever occupy by a standard symmetric rigid body. Remember, there we only had even J. In this case, we get a new kind of space consisting of odd angular momentum for this orthohydrogen. And likewise, there's a position state story here as well, which is what our contribution is. In the former case, we had equal superpositions with a plus coefficient, and now if you do the Fourier transform here, you have equal superposition with a minus coefficient. So both the momentum states, even and odd, are different, and the position states, of course, have to be different, and they're different by this sign. So what does this mean? Well, this has interesting consequences for another set of physical transformations that we care about in the lab, namely passive with respect to the molecule, or lab-based transformations. This is another set of transformations that reorients the frame of the lab that you're looking at the molecule in. So the molecule has its own frame, and the lab has its own frame, and each frame can transform under different sets of rotations. The molecule frame transformations that we just discussed determine the states of the molecule that are allowed by these symmetry and spin statistics constraints. The lab frame transformations act freely on the molecule, and both lab and molecules transformations have symmetries. And symmetry lab-based rotations act on the molecule in a very interesting way. So here we have our hydrogen molecule, and we have a symmetry transformation that's lab-based, which is different from the one in the molecule frame, because there, in the lab frame, it does not permute the nuclear spins. It happens to move the position of one of the nuclei to the position of the other, but because it's a passive transformation, it doesn't actively permute the nuclear spins. And so now you don't have a swap factor on the C2 guys. And in this case, the behavior is then species dependent. The paraspecies, so this symmetry transformation shifts phi to phi plus pi, because in the position space, that's what it does. It generates rotations in the position. And if you take your position states of the paraspecies and you apply this symmetry, you just exchange them. But if you take the position states of the orthospecies that are equal superpositions with a minus sign of the original position states of the asymmetric guy, then you get a minus sign. So you see that the two species transform differently. Remember, so we used molecule-based rotations to define the species to begin with, and now we're looking at how they transform under lab-based rotations. Okay? And they transform differently under the latter. And so how do they transform? Well, the way we think about it is that lab-based rotations form some symmetry group. In this case, again, just C2 or Z2. And each position state can be thought of as carrying a certain fiber. Now, literally, this is a fiber. And the fiber, in this case, it's a scalar. It transforms as some erep of the symmetry group under symmetry rotations. In the case of the paraspecies, the fiber is trivial, and so it just transforms under the trivial erep of the C2 group. In the case of the orthospecies, the fiber is non-trivial because of that minus, and it transforms as the sine erep of the symmetry group. And that's how these two things are different. So if we were to kind of graphically picture the things we just looked at, we looked at three examples. The first two are here. The first case is something completely asymmetric. There's no symmetry at all. And so it's just the orbit of the symmetry group, allowed group of transformations, which is SO2 of this object. In the case of the rotational symmetry, we have a pi symmetry, a 180-degree rotation symmetry. And so we have to quotient that out. And when we quotient that out, it just means we superpose the state and its antipode. And we get this SO2 mod C2 quotient, which is just basically another SO2, but it's a smaller SO2 because it goes from 0 to pi and includes only even momentum states. In the weird case, in the third case now, we have something that we have to use fiber bundles for. And now we have this little fiber guy transforming in this interesting way as the sine erep of the C2 symmetry group. The parametrization of the states is still the same, but now we have this extra -1 factor. And if you think of this transformation, this rotation, as something that's like an adiabatic movement, a slow movement in the quotient space, then this -1 can be thought of as what's called a Berry phase. in quantum mechanics. And in this case, the Berry phase is strictly -1. And it's an example of what's called a holonomy. Maybe that's the word that you guys are familiar with. Which one? Is anybody familiar with either term? Okay, good. So if you have a parameterized set of vectors, let's say in a space, and the parameters that are labeling the vectors are lying in some, in this case, quotient space, then when you move in a closed path in that space and you get back to the same point that you started in, your state might have a transformation that it undergoes. You go back to the original state, but you don't have to go there with the same phase. You may get a different phase after you go by this closed path, and the phase of the state will depend on the details of the path. This is an example of a scalar holonomy. If you now have a subspace that's parameterized by some parameter, and you move the subspace around, then at the end, you get back to the same subspace, but now you have a matrix acting on your subspace that changed your location within that subspace. That's an example of a vector holonomy, or just like a normal holonomy. Now, this Berry matrix or holonomy can depend on the details of the path. It depends on either the geometric details of the path, namely the curvature, the area enclosed, small variations in the path, or the topological details of the path, namely whether the path is simply connected or not. And in this case, in the case of this hydrogen molecule, it turns out that there's a Berry phase of -1, a holonomy, and this holonomy depends only on the fact that you went around the circle once. It depends only on the fact that you've enclosed this non-contractible path, and it doesn't depend on any other details. And a holonomy that only depends on the topological details of the path is called a monodromy. Okay, you may have heard monodromy in a different context, some differential equations and whatnot, but it basically means that your holonomy, or Berry phase in this case, is dependent only on the topological details of the path. And that'll be the kind of the highlight of our story here, because TLDR, for all the molecule state spaces that we've classified, all of our symmetry-induced transformations or holonomies are independent of any geometric details and only depend on the topology of the path. In this case, we have a circle that's our underlying space of our fiber bundle, and the fiber is the thing that's moving around. So the fiber is the set of states, or in this case, state that's parameterized by a quotient space, which is phi, the angle. In this case, our space is not simply connected, so we have a potential to have monodromies. But what's interesting is that we have a monodromy, and it's not, and there's no geometry involved, only topology. So that might have been a lot, and I maybe should have had an intro slide to monodromy, holonomy, but I'm just going to gauge to see if you guys are still with me. Okay, good. Yeah, math audience, awesome. So how do we classify all these state spaces? Well, the way we thought about it, okay, you can kind of do this as fiber bundles because it's basically the same kind of data, but we have a specific set of fiber bundles that are labeled by group data. The base is a quotient of the allowed transformations by the symmetry group. In this case, we just have circles everywhere because we're just quotienting C2 by SO2 in the case of C2 symmetry. And then the fiber is an EREP, transforms as an EREP of lab-based rotations, some EREP of the symmetry group G, gamma rotation, gamma rot. So in the case of the exotic guy, the perrotational guy, where we have permutation and rotation symmetry, the EREP is B, the sign EREP, that way chemists call the sign EREP. By the way, chemists call the trivial EREP different names depending on the group. I was about to scream when I saw that first. They call it either A or A1. So anyway, the sine irrep is also sometimes called A2, sometimes called B. Yeah, we had to go through that. So in this case, it's called B. And then so in this case, the inducing irrep is B up arrow SO2. Okay. The inducing irrep is B, and the induced representation of SO2 is B up arrow SO2 or ind C2 SO2B. So we've only looked at asymmetric guys and C2 symmetric guys. So the asymmetric guy doesn't transform like anything because if I rotate my pen, I don't get a -1 flying out, right? The C2 symmetric guy can transform trivially like a dumbbell, but it can also transform non-trivial like this ortho case. C3 symmetry gives you even more interesting things, even when we're only in 2D. In C3 now, you have your fidget spinners that don't transform as anything. They just parameterize regular quotient spaces. But now if you have boron trifluoride, which has 3 fluoride nuclei, those have to be permuted and satisfy spin statistics. And there's irreps of C3 involved, which have cube roots of unity. And now when you do a lab-based transformation by 120 degrees of that guy, you get a phase of e to the I 2 pi over 3. So even in 2 dimensions, when you're lying on a table, if you rotate these molecules in this way, you get phases that you cannot get using ordinary bosons or fermions. You get phases that are essentially the same kind of phases you get when you braid non-abelian anyons. And this induced representation picture, the math here is the same. We have holonomies, either from rotating or from braiding. We have the fact that they're monodromies, meaning they only depend on the topology of the path and not the geometry. And then we have a group realized here. That's just the quotient of the symmetry group by the inducing irrep. And in both cases, both abelian anyons and this kind of stuff is described in the same way. The groups are different. In this case, the groups are subgroups of SO2. In the case of anyons, they're subgroups of the braid group, but the math is the same other than that. So our main result is from going to 2D to 3D. And basically the story is the same, but everything becomes more complicated because things become non-abelian. So our assumptions, so molecules have a lot of degrees of freedom. So our assumptions were that everything except the minimal set of degrees of freedom that we had to account for in our spin statistics is decoupled. The orbital degrees of freedom, the vibrational degrees of freedom, and the electronic spin degrees of freedom are all decoupled. And that leaves us with rotations and nuclear spins. And the reason we can't just decouple those and just work with the rotations to get our Fourier transform is because, as you may recall, molecule-based symmetries affect both the rotational and the nuclear spin factor. They act as an L2 of SO3 left regular representation on the rotations, and they act as a permutation representation on the nuclear spin factors. Okay, so we have this composite action we have to take into account for. And so we can't decouple the rotation of the nuclear spin, and this gives you the minimal kind of model for these Fourier transforms. So, and again, we basically had the same kind of 3 classes. We had the case when you had no rigid body symmetry, so we're just in L2 of SO3. There may be some spinful nuclei, and they may even be identical, but there's no transformation in SO3 that transforms them in a way that leaves the molecule orientations the same as you started with. So we don't care about them. They're just the dangling singlet of the parahydrogen. The second case is when we have symmetry, but we don't have any identical spinful nuclei. For example, sulfur doesn't have any nuclear spin. C60 doesn't have any nuclear spin. So those have the same state space as a dumbbell and a soccer ball. Okay. And HCl also has a SO2 symmetry along its dominant axis. So it also falls into this class in 3D, right? So it's a pencil. Things get very interesting when you get these fiber structures, these induced representations, when you have identical nuclear spins and when you have them permuted by symmetry. So H2 we already covered, but BF3 we already covered. These would be the 3D versions of these. Now you can have things that, you can have 3D transformations. So BF3 now the symmetry group is D3, dihedral group, as opposed to C3, which is what it was only in 2D. And then you have these other atoms like or other molecules like water, and even a variant of C60 where you've translated or transformed all the carbons to carbon 13s. Those have nuclear spin. And then you have this whole situation where you have 60 different nuclear spins being permuted in some way under the icosahedral symmetry of this molecule. And this is a permutation rotational symmetric molecule or perrotational symmetric molecule. And the main result is, hopefully as you would expect, the rotational state space of G-symmetric molecular species transforms as an induced representation, gamma rot for some E-rep of the symmetry group G. And the induced representation is over lab-based or passive transformations. And all three of these classes can be expressed as induced representations. The asymmetric class is just your standard rigid body, so L2 of SO3, so Peter-Weil theorem. The rotational symmetry class is just your vanilla quotient space. So in the case of HCl, it's SO3 mod S2. It's the quotient space, SO3 mod SO2. It's just the two-sphere. So states of HCl are parameterized by a two-sphere. S2 is just RP2, which is SO3 mod O2, because you have this extra flip transformation. And so that's just RP2. And there's no weird fibers going on. It's just the vanilla quotient space and no extra degrees of freedom. In the perrotational symmetry class, you have an inducing E-rep. The E-rep, if it's scalar, it means the fiber will transform and give you some sign or some root of unity. But now, because we're in SO3, the E-rep gamma rot can be vector. And now our fibers gain space to store quantum information. And this is the surprising fact that we kind of bring to the table, is that when we have symmetric molecules of the type of the perrotational type, every orientation of the molecule carries with it a pseudo-spin or a fiber degree of freedom that is required to label all of the different position states of the molecule. And moreover, this fiber degree of freedom transforms very non-trivially, aka in a topological way, under lab-based transformations. So to get the Fourier transform in this induced representation space, I could have learned Mackey theory, but I didn't because it was hard. And so I tried to express this in a way that people usually express these things in terms of a duality. Here's some momentum states, here's some position states, and here's one in terms of the other and vice versa. So the momentum state picture, as I mentioned, has been worked out to death by chemists. We were not aware that anybody realized this was an induced representation of SO3, so that's our main contribution. But in the momentum side, what you have in the chemistry jargon is you have J total momentum. In math, that's E-rep of SO3 that's present in this induced representation. M is the z-axis projection into the lab frame. In math, that's the internal index of that E-rep J. So J is some subset of the non-negative integers, which are E-rep labels of SO3. And then there's a third index that rides along sometimes, which is kappa, which is the multiplicity of the inducing E-rep in that particular J subspace. If you were to get here from Peter-Weil, so Peter-Weil, the J and the M indices are the same. You have the E-rep index of SO3, its internal E-rep index, and then instead of kappa, you'd have this kind of M prime index that would index the right regular representation. Anyway, but if you don't know what I'm talking about, it doesn't matter. And then you could have proven this using some kind of Frobenius reciprocity or Mackey theory, but I write this as a physicist. I write the position basis in terms of the momentum basis. So what you do is you take superpositions of momentum states to give you states of fixed orientation. So the position side, you have a position state index, which lies in the quotient space of SO3 mod G. But now I told you you have this fiber, and we index the fiber degrees of freedom by mu. They go from 1 to the dimension of the inducing E-rep, which is D, which is this frac D. Okay, so now the weird part is that you have two indices for position states, the base and the fiber. And when frac D is 1, there's no index for the fiber, but there could still be a non-trivial fiber, it'd just be a scalar. But when frac D is greater than 1, aka when the inducing E-rep is non-abelian, is a vector E-rep, this fiber has an index. And the two sides are basically, can be expressed in terms of one or the other by superposing one to get the other and vice versa. And the coefficients there are these harmonics. There's particular sets of harmonics on these E-rep space, on these induced representations that I can show you. There's a recipe how to get them from the Wigner D matrices, which are the basic harmonics from the Peter-Weil theorem. Right, so I really wish people in math would have written it like this, like 50 years ago, because it would have saved me a lot of time. But the equivalent expressions that I see for this involve, res and ind and categories and functors and very abstract things. So this is the practical way that I think is useful to write it. Okay, so as I mentioned, we have these orientations, we have these fibers, and the fibers themselves transform non-trivially in a topological way under lab-based symmetry rotations. And moreover, in this version 3 of this paper, we show that the fibers not only have non-trivial transformations, which you can think of as gates on the logical information stored inside the fiber, but you can also show that the fiber itself is intrinsically protected against some type of noise on the molecule. So the fiber itself can be thought of as an error-correcting code. And what's interesting is that this fiber lives in a single molecular orientation. And what typically happens in error correction is to really get a good code, you have to take superpositions of whatever basis you use to define the state space. So previously we had we showed a recipe to produce particular superpositions of different orientations of an asymmetric molecule to give us a good code that we called a molecular code. That involved several orientations. In this case, this kind of protection or a similar protection is happening in what seemed to be a classical state of an orientation of a molecule. But because of the interplay of spin statistics and symmetry, this is no longer as classical as you might have expected, and it carries with it this super delocalized and somewhat protected in a topological way degree of freedom. So I'll spare you the error correction details, but I will mention, but I'll jump to the monodromy, I'll jump to the logical gates. Remember, if we go around our closed path in this parameter space, which is SO3 mod G, we get back to the same A. So our A will be identified, our quotient space point will be identified with the final space point that we got to. But that identification will then induce a monodromy, a matrix valued monodromy, that is this gamma rotation that acts on our internal mu nu labeled spin degree or fiber degree of freedom. So we show that this kind of monodromy occurs for all of our molecules, all the molecules that are classified by our formalism. Now, how do we show this? Well, we calculated the Berry phase that you get, or the holonomy, the full kind of this. It's just some cranking out some calculation to get the actual Berry matrix or Berry phase that you get from these spaces. We can calculate this explicitly using various techniques. And we get 0 for the generator of the Berry matrix, which is called the Berry connection. This Berry connection gives us 0, meaning the connection is locally flat. Why locally? Because remember, when we do these kind of global non-contractible loops, we get this monodromy. But the monodromy doesn't come from a Berry connection in the way we calculated it. It comes from like a reparameterization of the final quotient space coordinate with respect to the initial one. So the monodromy is separate from this calculation, and this calculation only determines the geometric contributions of the phase. And we get 0. We get no non-topological contributions to the phase. And so here's all our different species. that we had for the molecules. So for symmetry groups, first column, there's certain species that we can label. The inducing Europe dimension is the third column. Most of them are one, but some of them are more than one. And then the connection turns out to be flat. The Berry connection is, by explicit calculation, 0. But it's for different reasons. And we don't, we conjecture that all these different reasons can alternatively be explained by a coincidence that we noticed between the Berry connection and what's called the G connection on this fiber bundle, which is related to the Maurer-Cartan connection. So there's basically kind of two types of connections on these spaces. One is our Berry connection that determines how molecules rotate and how they transform. And one is this mathematical G connection that just relates to projecting the SO3 Lie algebra into this induced representation. And we noticed, for all the examples that we've seen, one is flat if and only if the other is flat. Namely, one is 0 if and only if the other one is 0. Okay? And we don't know why, but we can conjecture. So here's the conjecture. So again, our Berry connection, which is this kind of overlap with respect to our position states, but now we're taking derivatives of the position state and then overlapping it with itself for different internal fiber indices mu nu. It's just something we can calculate as physicists, okay? And then from this, we can determine that it's flat, and we can determine the monodromy, not the mudromy. On the other hand, you have this stuff the rep theorists know. You have these G connections. And these G connections are classified. They've been classified for a long time by mathematicians. They're classified by E-reps of the fundamental group of the quotient space. So in this case, the conjecture is more general than SO3, so I'm substituting a general Lie group K for SO3. And so on this side, the story is known. The G connections are classified by E-reps of the fundamental group of the quotient space. Fine. When we do our calculation on the left-hand side, and we write the Berry connection A, we can express it in terms of two terms. One is the G connection, and the other one is some residual term. Okay? So the two connections are related, but they're not equal because there's this other perp term. Okay? But in all the cases we've noticed is that all three terms are 0 if and only if the following holds. Namely, if the data on the left-hand side coming in from the induced representation matches some form of data on the right-hand side. So on the left-hand side of this equation 156, we have the induced irrep data. This is our monodromy group. You take the inducing irrep, gamma, which used to be gamma rho. You quotient the symmetry group G by its kernel, and you get a group. Okay? That's called that's what we call the monodromy group. For the case of parahydrogen, the irrep was the trivial irrep, the group was C2. So the kernel of the trivial irrep is C2. So you have C2 divided by C2, which is just nothing. It's just the trivial group. For the case of the other hydrogen, the symmetry group was C2. The kernel of the irrep then was the sign irrep. The kernel was just the identity element. So it's faithful. So it's C2 divided by C1, which is just C2. Okay. That's the left-hand side. So the G divided by Kerr or gamma, that's our induced rep data that we get from the Berry calculation. On the right-hand side, we have the fundamental group and its irrep rho. And the conjecture seems to hold so far, whenever for a given G and gamma, we pick a rho such that the quotient of pi 1 by kernel of rho matches the quotient of G mod kernel of gamma. Okay? So that's the conjecture. And I'll show you some examples of it that, should be familiar. One is just this C13C60 buckyball guy. So here, K is SO3. We're back to molecules. G is the icosahedral group I, 60 elements. The coset space is the Poincare sphere, SO3 mod I. The fundamental group of the Poincare sphere is 2I, the double cover of the icosahedral group, the binary icosahedral group. And now, remember 156, we have to see if we can, we're given the information on the left-hand side, and now we have to see if we can pick a row that matches the information on the left-hand side. So our gamma is any E-rep of I. So we have G mod kernel gamma. I happens to be a simple group, which means that the kernel of gamma is always trivial, the identity element. So no matter which gamma you pick, I divided by kernel gamma will be I for any non-trivial gamma. So then equation 160, we just have I by kernel gamma equals I. So we get I on the left-hand side no matter what we do. And now we have to pick a row from the fundamental group to match that. Well, we can just take our gamma element and upgrade it from an I rep to a 2I rep by assigning -1 to the kernel, by mapping all of the -1 elements of the 2I group to the kernel, to trivial. And so from gamma, we get this 2 kernel gamma, or kernel 2 gamma, what have you. And we mod 2I by that, and we get the same thing. We get I. So the 2's cancel, basically. That's my physics explanation. So this is one example where this kind of holds. It's semi-trivial. Here's another one. This is more familiar, actually. This is this sphere. K is SO3. G is SO2, or C infinity, as the chemists call it. The coset space is SO3 mod SO2, which is the 2-sphere S2. The fundamental group of the 2-sphere is C1. It's trivial. So on the right-hand side, the only row we can pick is A, the trivial rep. So we don't have any freedom in row. We're done. It's just C1 for the right-hand side. So now we have to see which induced reps match that structure. So for the left-hand side, we pick a gamma and see if it matches. First gamma we pick of C infinity is the trivial rep. Well, the trivial rep maps everything to 1, so its kernel is the group itself. So it's C infinity mod C infinity, which is just C1. We match, and it works. The connection for this space is flat, both the Berry and the G connection. What about the other E-reps? The other E-reps are labeled by a non-zero integer of C infinity. And they have a kernel that's like mod whatever. Some of the stuff comes into the kernel as soon as, because the lambda is the power of, e to the I lambda phi, for phi being an element of U1. So the lambda will wrap around, so you get our different circles, basically. And, no matter what, so we get some kernel. There's going to be some like Z lambda subgroup. I don't know why I took the absolute value of it. But in whatever lambda is, as long as it's non-zero, the quotient of C infinity by C lambda is still basically C infinity. It's the same kind of math as we had for our circles. And so we get C infinity on the left-hand side and C1 on the right-hand side, not satisfied. So what do all these cases correspond to? Well, these cases in physics, they correspond to spheres with monopoles of strength lambda. So this induced representation shenanigans can be used to label what are called monopole spheres with monopoles in them, and literally the strength of the monopole is the index of the E-rep that's inducing these transformations. And in several fields, these induced representations and their associated harmonics are called spin-wave spherical harmonics, and this is called a spin-wave representation. And if lambda goes to 0, we get our ordinary spherical harmonics, and all the Berry connections are 0. The Berry connection is 0, and we get back to satisfying our conjecture. So that's right. So that's our conjecture. I really wanted to get that out there. Hopes if somebody can actually prove this or disprove it. There's more examples in the paper. So this correspondence that we've noticed so far is as follows. We have this fiber degree of freedom in our molecules. We show that it transforms in a non-trivial way. And in quantum information, you can then assign states in that fiber to encode logical information, and you can associate the monodromies that you get from these symmetry transformations with gates. And turns out that this is a general part of a general family of examples where this is true in both quantum information and condensed matter physics. In quantum information, there's a conjecture that if you have a set of gates that you can do on a code, on an encoded subspace, if those gates are what's called fault-tolerant, which means they're protected in some way, then there should be a way for you to understand those gates as a monodromy, as a holonomy that only comes from topological features. And this is exactly what we see here. So we have an example of this kind of holonomy and monodromy, as I showed you before, correspondence. But there's a few other families of things that came before us that also noticed this. So in one case, in condensed matter, quantum Hall wave functions, namely these braiding of these anyons, abelian anyons, also can be thought of as a monodromy, as I mentioned before. More recently, the picture on the right-hand side, there's a class of error-correcting codes that consist of lattices, superposition of points in lattices in L2 of R to the n. And those codes, gates on them can be thought of as moving in the space of lattices, which is a non-simply connected space. And you can think of doing the gates as moving in a closed loop in this non-simply connected space. And the effect of the gate on the code is a monodromy. This paper from 2013 in the corner on the left here really formalizes this from a mathematical perspective and conjectures this and makes the main conjecture that I'm mentioning here in the case of error correcting codes. So this is kind of interesting that we see this in molecules. It's not somewhere I would have expected to see it, but again, the math is all the same in all of these cases. So just to summarize, we developed this position momentum Fourier duality for certain types of molecules. You'd be hard-pressed to find an application that doesn't include Fourier duality in it. So we hope that hopefully as people begin to control these molecules better, they'll be utilizing this for protocols and gadgets. I mentioned that we have to technically work in a rigged Hilbert space, but this is like using an integral to calculate a sum. It's not a big deal. We're looking at how to extend this to incorporate other degrees of freedom. And I mentioned that these fibers now that are present in these orientations, they have this topological behavior under these lab-based transformations. So you can think of them as fault-tolerant gates on any encoded information in this fiber. It would be nice to realize this experimentally, but we're a bit far from that as far as I can tell. And then I had like 6 or 10 more, maybe 6 more slides about the proof details, about how we got to this induced representation to begin with. But I probably will lean to just ending here and maybe having a discussion instead. So with that, well, how much time do I have actually?
I think that's a good stopping point.
Yeah, okay.
Yeah.
So that I'll thank you for your attention and thank you for this opportunity.
Yeah, thanks so much. All right. I'm going to hit this reaction button for me and Dustin. Do that thing, and I encourage everyone else to do the same.
Well, nobody asked any questions, so